So trigonometric functions are defined using a right triangle. So the domain of a trigonometric function is going to be an angle and our range is going to be the ratios of the sides of a right triangle. So our trigonometric functions are defined in terms of some angle, and then the output is going to be the ratios of the sides of a triangle. And so since we're talking about ratios once again, we're going to end up with our range being a pure number. Because the sides of our triangle are both going to have units of distance, and they will reduce out when we divide, aka we make their ratio. So we're going to define all 6 of our trigonometric functions in terms of this. So they're summarized on this sheet, and we have the following. So our definition of the sine function, the sine of the angle theta, is the ratio of the opposite side of theta and the hypotenuse. So talking about our anatomy here, we have our angle theta. The opposite side is going to be the side across from the angle theta. Adjacent is going to be the side of the triangle next to the angle theta. And the hypotenuse is always the angle, or the side across from the right angle. So by definition, our sine of theta is going to be opposite over hypotenuse. The cosine of theta, with symbol COS, is the adjacent side divided by the hypotenuse. Tangent is the opposite side divided by the adjacent. And then we have our 3 co-functions, and we'll talk more about these a little bit later in depth and why they're called the co-functions. They're also called the reciprocal functions because the cosecant is 1 divided by sine, or the reciprocal of sine. So sine is opposite over hypotenuse, so the reciprocal would be hypotenuse over opposite. Similarly, secant is 1 over cosine, or hypotenuse over adjacent, and cotangent is 1 over tangent, which would be the reciprocal and would be adjacent over opposite. So we are going to need to memorize these 6 things. They are the fundamental basis for right triangle trigonometry. So we're going to need to know these definitions of sine, cosine, tangent, cosecant, secant, and cotangent. We have 2 special triangles that we want to talk about, and you're probably saying, well, Professor Peterson, I count 4 triangles. The reason I say 2 is the 2 pairs are actually the same triangles. It's just one of them is written in terms of degrees, and the other is written in terms of radians. So in these triangles, 60 degrees is the same as pi over 3 radians, and 30 degrees is the same as pi over 6 radians. So these are really the same triangle. The same is true for 45 degrees is the same as pi over 4 radians. So these 2 triangles are actually the same. So there's really only 2 triangles here. It's just one has their angles in terms of degree measure, where the other has them in the proper measure of radians. So in terms of these triangles then, we can figure out some of our trigonometric ratios. So before we do that, if I asked then, for instance, well, what is the sine of pi divided by 6, what would you tell me? Well, I would go find my angle, pi over 6, which is the same as 30 degrees. And by definition, we know that sine is the opposite of theta divided by its hypotenuse. So it's going to be the opposite of theta divided by the hypotenuse. So the side opposite of our theta is going to be down here is 1, and the hypotenuse is 2. So the sine of pi divided by 6 is equal to 1/2. So we can use these special triangles to calculate the exact values of some of our trigonometric ratios. So then, for example, if I did the cosine of pi over 6, I'm going to use that same angle, but by definition, cosine is adjacent theta divided by the hypotenuse. So our side adjacent to theta is going to be the square root of 3, and the hypotenuse is still 2. So this is often referred to as the exact value. So the exact value of the cosine of pi over 6 is the square root of 3 divided by 2. All right, let's try a few more examples. So at the top of the next page, we have the following. We're told that the sine of beta is equal to 12 over 13, and that the cosine of beta is 5 over 13. We want to find the tangent of beta, the cosecant of beta, and the secant of beta. So we need to construct a triangle. So I'm going to draw a triangle, and I label my known angle. And when I say my known angle, I mean the angle of these that was given. So we're going to call this beta. And we know sine beta, sine by definition is the opposite of theta divided by the hypotenuse. And we also know that this is equal to 12 over 13. So the side opposite of beta is going to be this side of my triangle. So the length of that side has to be the number 12. The hypotenuse is always the side across from the right angle. That's going to be here. And our hypotenuse is going to have to be 13. We were also told that the cosine of beta, which we know is the adjacent, beta divided by the hypotenuse, and we're told that that is 5, so then that means the adjacent side would have to be the number 5. Well, we now know all three sides of this triangle. So then the tangent of beta is the opposite over the adjacent. So our opposite of beta is 12, and our adjacent to beta is 5. So the tangent of beta would be 12/5. Our next one is the cosecant of beta. So cosecant is 1 over sine, or hypotenuse over opposite. And our hypotenuse is 13. And our opposite is 12. So the cosecant of beta would be 13 over 12. Notice that is the reciprocal of this. And we knew that the definition of cosecant was 1 over sine. So if we take the reciprocal of 12/13, we get 13 over 12. And lastly, we have secant, which we knew is 1 over the cosine. And 1 over the cosine is 1 over 5 over 13. So that would be 1 over 1 times 13 over 5 is 13 over 5. Or, directly by the definition, we know it's going to be hypotenuse over adjacent. And the hypotenuse is still 13, and the adjacent is still 5. And we get the same value. So we can define our trigonometric ratios as the reciprocals, or by the base definition, which was just hypotenuse over adjacent in this case. So we have the following theorem, which relates our tangent function to sines and cosines. So we have the following relationship. So let's start with sine x over cosine x, which would then equal to, well, sine, by definition, is opposite over hypotenuse. And cosine, by definition, is adjacent over hypotenuse. But if we have a fraction divided by a fraction, it's the same as multiplying by the reciprocal. So we have opposite x over hypotenuse times the reciprocal of the denominator, so that'll give us the hypotenuse over adjacent. And we have hypotenuse and hypotenuse reduce out, which then gives us the opposite of x divided by the adjacent of x. But that, if we go back to our chart, is exactly the definition of our tangent function. Tangent is defined to be opposite over adjacent. So then this is the tangent of x by definition. So we have that tangent of x is the same as sine over cosine, or sine over cosine is the same as tangent. As a corollary, we know that 1 over tangent is equal to cosine. So, or cotangent. So 1 over tangent x is equal to cotangent x. Well, that's the reciprocal of tangent, so that would imply then that the cotangent of x is equal to the reciprocal of sine over cosine. So cosine x over sine x. So we have those following relationships for tangent and cotangent. So tangent is sine over cosine, and cotangent is cosine over sine. So let's take a look at example number 2. It wants us to find the sine of both triangles. So for our small triangle, this guy right here, we're going to have that the sine of theta is going to be equal to opposite over hypotenuse, so 3 over 5. And if we take a look at our bigger triangle, that's this guy, and we take the sine of theta, we're going to have our opposite, which is 6 over our hypotenuse, which is 10. But 6/10 reduces to 3 over 5. So we're going to notice that these two values are the same. But the real question is, well, why did they work out to be the same? Well, if this angle is theta in both triangles, and this is a right angle, then we have the following relationship then. The two triangles, then all three angles must be equal. Or our fancy geometric word for that is congruent. So then, from geometry, by angle, 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 the two triangles are similar. And recall, from geometry, if two triangles are similar, the ratios of their sides are proportional. Strictly speaking, they're directly proportional. So that would mean their side lengths are related by an equation y equals k times x. Well, if that's the case, we'll notice, well, indeed, 10 is 2 times 5, 2 times 4, and 2 times 3. So our proportionality constant in each of those cases is 2. But regardless, if they're directly proportional, if we form a ratio, what's going to happen each time? Well, that common factor of 2 is going to reduce out every single time. So the important part about all of this is that similar triangles have the same trigonometric ratios. So that's good. So that means if we have any two triangles, that the trigonometric values are going to be unique up to this similarity, which is nice. Otherwise, we would have a really big mess. So what we really need to know about this is that similar triangles will always have the same trigonometric ratios. All right, so example 3. Let's find the sine 30, cosine 30, and tangent of 30 degrees. So in order to do this, we're going to need one of our special triangles. So we go back, and we need the special triangle that has the measure of 30 degrees in it. So that's going to be this first triangle. So in terms of our trigonometric ratios then, we have our 30 degrees right here, which is what we're interested in. So then that would make this side the opposite, and this side would be adjacent. And the side across from the right angle would be our hypotenuse. So then our sine of 30 degrees, by definition, sine is opposite over hypotenuse. So our sine of 30 degrees is going to be 1 over 2. The cosine of 30 degrees is going to be adjacent over hypotenuse. So that's going to be the square root of 3 over 2. And then tangent of 30 degrees is opposite over adjacent. So 1 over the square root of 3. But then here we have a little bit of a problem. We must rationalize the denominator. So we build our fraction by multiplying the top and the bottom by the square root of 3. And that gives us root 3 over 3. So then our tangent 30 degrees is the square root of 3 over 3. It's also worth noting that tangent 30 degrees is equal to sine 30 divided by cosine 30, which we'd already calculated, so it's 1/2 divided by root 3 over 2. So 1/2 times its reciprocal, 2 square roots of 3. Our 2's reduce out, and we get 1 over the square root of 3, which is exactly the same thing we had here. So either way, we get that same value, which would then rationalize to the square root of 3 over 3. So it's worth noting that that's really just two different ways to write the same thing, right? If I take 1 divided by the square root of 3, I get that number. And if I take the square root of 3, I get the same decimal approximation when I divide it this way. So rationalizing the denominator is like having good grammar in mathematics. Both of them are mathematically equivalent. 1 over the square root of 3 is equivalent mathematically to root 3 over 3, but it is considered improper to leave radicals in the denominator. So the convention is that we always rationalize the denominator, putting the irrational number and the radical in the numerator. So as decimals, they will always be equivalent, but this one is the proper way to write it, aka having proper math grammar. All right. It's now your turn. So please go ahead and simplify the following values. All right, so let's go ahead and resolve this. So if we grab our reference triangle, we have our following, and we want to find the sine, the cosine, and the tangent of pi over 3. So the sine of pi over 3 is going to equal, well, sine is opposite over hypotenuse, so we're going to get root 3 over 2. The cosine of pi over 3 is going to be adjacent over hypotenuse, so that's going to give us 1 over 2. And the tangent of pi over 3 is equal to opposite over adjacent, so that's going to be root 3 over 1, or the square root of 3. So those are the values of our 3 trigonometric functions at each, or at the angle pi over 3 radians. So a couple of things we want to take note of with these in our calculator. So if we grab our calculator, we'll notice that the fourth row down from the top of our calculator, right in the middle, we have sine, we have cosine, and we have tangent. So let's go ahead and press the sine button. And if I go pi divided by 3, I get this value, and let's check. So I go the square root of 3, and I divide it by 2. So I get the same decimal approximation on my calculator for each of these values. So this tells us a couple of things. So once again, this is our exact value. So when you're asked for the exact value, you need the one involving the radical. So the root 3 over 2, this is an approximation. So oftentimes you will be asked for the exact value, not the approximation that your calculator will give you. Second thing that this tells us is, note, the calculator is in radian mode, right? So if we go back to the previous example, when we were doing things like sine 30 degrees, if I type sine 30 into my calculator, what do I get? Well, negative 0.98803. What was I supposed to get? 1/2. This is because my calculator is in radian mode, not degree mode. So if we look right here at the top of our calculator, just to the right of our second button, we have our mode key. If you press that, you'll notice the third choice down, by default, unless somebody has changed it, our graphing calculator will always be in radian mode. So if we need to do computations in degrees, we have to change our calculator from radians to degrees. Then, if I type sine 30 degrees, I get 0.5, which is indeed 1/2, which is what it's supposed to be. So one of the most common mistakes that we're going to run into, especially in the beginning, is we're going to be switching our calculator between degrees and radians. Always make sure your calculator is in the right mode. For the most part, we will work in radians, but you will see problems in both. So be sure, if you need to do a computation in degrees, that your calculator is in degree mode. If you're doing computations in radians, you need to have your calculator in radian mode. Or, as we just saw here, it will give you the wrong number if you're not in the right mode. So if you keep missing a problem when you're putting it into your calculator, that would be the first thing that I would check. Make sure your calculator is in the right mode. All right, so building on what we just saw there, two angles are complementary if their sum is a right angle. So either 90 degrees or its radian equivalent, pi divided by 2. So looking back at the previous example in UTRI, we noticed that 30 degrees and pi over 3 are complementary angles. Because pi over 3 is 60 degrees, and 30 degrees is pi over 6 radians. So if we add pi over 6 plus pi over 3, well, that's pi over 6 plus getting a common denominator, 2 pi over 6. So that's 3 pi over 6, which is pi over 2. So our two angles are complementary. So two angles are complementary if they add up to a right angle or 90 degrees. Well, let's look at each of these. So I'm going to convert my 30 degrees to pi over 6, and we had that the sine of 30 degrees, or pi over 6, was 1/2. We had the cosine of pi over 6 was root 3 over 2, and we had the tangent of pi over 6 was 1 over the square root of 3, which is the same as the square root of 3 over 3. And we now want to look at the ones you just did. So in your you try, we did sine pi over 3. And we got root 3 over 2. We did the cosine of pi over 3, and we got 1/2. And we had the cotangent of pi over 3, which we got the square root of 3. So what do we notice about each of these? So the sine of pi over 6 equals to 1/2, and the cosine of pi over 3 equals to 1/2. The cosine of pi over 6 equals root 3 over 2, and the sine of pi over 3 is equal to 3 over 2. We notice that the function and its cofunction, sine and cosine, have the same values at the complementary angles. So the co comes from complementary. So cofunctions. So cosine and cosine comes from the co in complementary. So we're going to have this relationship. Specifically, the relationship is this. We have the following, which are our cofunction identities. So, remember, two angles are complementary if they add up to 90 degrees or pi over 2. So pi over 2 minus x plus x, those cancel out, we get pi over 2. So our cofunction identities say the following. The sine of pi over 2 minus x is cosine, and so forth. All right. So let's use that to simplify few things. So if we know that the sine of alpha is 1 over 6, we want to find the cosine of pi over 2 minus alpha. Well, that's going to be exactly this identity. So this tells us that if the cosine of pi over 2 minus alpha is the same as sine alpha. Well, we know sine alpha, so this is really just 1/6 by the cofunction identities. All right, so these two angles are complementary. So then they have the same value. So it's going to be 1 plus the square root of 2 under the radical over 2. Because they're complementary angles just like in the previous example. All right. If we take a look at example number 5, we have the following. We want to find the unknown sides of this triangle. So we want to know A and C, but all we know is 4, and this is opposite pi over 3. So then, if we wanted to solve for A, we would have, well, opposite and A is adjacent. So then that would tell us that the tangent of pi over 3 is equal to the opposite, which is 4, over the adjacent, which is A. So cross-multiplying, we would get A times the tangent of pi over 3 is equal to 4. And we divide by tangent pi over 3 and divide by tangent pi over 3 to get A is equal to 4 divided by the tangent of pi over 3. So then we can calculate the tangent of pi over 3 by using one of our special triangles. So pi over 3 is going to be our 1, 2, square root of 3 triangle. So then that would give us 4, and tangent is opposite over adjacent, so square root of 3 over 1. So we would get 4 square roots of 3, or rationalizing, we would get 4 root 3 over 3. Similarly, if we wanted to solve for C, we would have opposite and hypotenuse. Well, opposite and hypotenuse give us sine. So the sine of pi over 3 is equal to our opposite, which is 4, over our hypotenuse C. Similarly, that gives us C is equal to 4 divided by sine pi over 3. This time, sine is opposite over hypotenuse. So C is equal to 4 divided by root 3 over 2. So that's 4 over 1 times the reciprocal. So that's 8 over root 3. Building our fraction, we would get 8 square roots of 3 all over 3. So we can find the opposite sides of our triangles by, or our unknown sides by using our trigonometric ratios. Go ahead and